And now please welcome Dr. Canan Dagdeviren for our second quick hit session, The Pacemaker Meets its Match. And I think Dr. Stein might be interested in listening more to this one. Canan, thank you.
Good afternoon. My name is Canan. It's a great pleasure to be here. Thanks for having me here. I'm a fresh PhD. I just received my PhD from the University of Illinois, Urbana-Champaign. And I'm currently a postdoctoral researcher at MIT working with Robert Langer. Today I will tell you a portion of my PhD adventure, a device which is flexible and conformable. It's kind of a tape that you can place this device on your heart or your internal organs, and it can capture mechanical energy and convert into electrical energy to power your medical implants. I'm a physicist, material scientist, and device engineer. The relationship between my research and heart is personal. When I was 5 years old, I learned that my granddad had passed away from heart failure at the age of 28. And I promised myself to do something for heart patients, and I set my dream age as 28, and I did it. My research was completed, and it was published in PNAS, and it was recognized by the Illinois Innovation Prize. And recently, I have been named as Innovator of the Year 2014 by MIT Technology Review. Outline. First, I will tell background and motivation of my study and go on with results and conclusion. The heart is not only a symbol of romance, it is also a hardworking and vital organ to maintain human life. It has to beat all the time. Out of 40 million heartbeats in a year, missing just a few can end your life. Imagine the heart as a real human dynamo. Every heartbeat of yours can be used to generate electricity. From the natural motion of internal organs such as heart, lungs, and diaphragm, mechanical energy can be harnessed to power medical implants. Active implantable biomedical devices rely on battery power. When the batteries are depleted, the devices must be removed. I have focused on the operational cardiac pacemakers, extending battery life of a pacemaker, or eliminating the need for replacement would spare patients from repeated operations and any resulting surgical complications. Pacemakers are not always active, but when a heart stops beating, they are vitally important. I have developed a device with a battery that never needs to be replaced and is powered by the heart's own motion, a simple heartbeat. As a material scientist, I have been working on new ways to use rigid piezoelectric materials. What does piezoelectric mean? A piezoelectric material is a crystal that generates voltage and current when it is mechanically deformed. I can make piezo devices in soft, flexy, stretchy tissue-like configurations by exploiting novel microfabrication techniques and tricks. My devices can take the shape of any human tissue. This is a new biocompatible mechanical energy harvesters. Device is malleable and can be laminated on heart as well as on other soft tissues. Here is the heart with my device. Under the rhythmic contraction of heart muscle, device bends and relaxes, enabling it to supply enough charge to satisfy for the needs of a pacemaker. By the way, in case you are wondering, this is the heart of a cow. Every people resemble their countries a bit. I'm originally from Istanbul, a city which connects two different continents, Asia and Europe, via a bridge. I'm also a bridge. I bridge the gap between today's electronic to 6 orders of magnitude compared to soft tissue in human body. The direction of the research, my research is motivated by an observation that all known forms of biology are soft, elastic, curvilinear, and time dynamic, whereas all known forms of electronic technology are rigid, planar, and brittle. As a result, there are few challenges in mechanics mismatch and geometric performance match when you want to integrate these two systems. Since we cannot change the biology, as a material scientist, I come up with new ways to use active devices, active materials, which have the shape and mechanical properties that match those of human tissues, such as heart, in order to allow intimate integration in between to create high efficiency devices. How do I do these things? This is the schematic illustration of the fabrication steps that I follow. First, I use a silicon backbone mono substrate, and I fabricate all my devices in an array form on the top of this silicon substrate. The key element of component of my device is an active component piezoelectric material, PZT, with top and bottom electrode as a capacitor form, and I have a sacrificial layer underneath. After all this, I protect all my devices with a polymer material and undercut the sacrificial layer with an acidic solution. Later on, the trick is coming. This step involves a transfer printing technique, a step, where I pick all my devices with a rubber stem and without any fracture from the out of this mono substrate, and then print on the target substrate, which is polyimide by a compatible polymer in this case. This is the resulting PZT mechanical energy harvester, which I will call PZT-MEH from now on. So I encapsulate all these devices in another polyimide thin layer to isolate the device from body fluids and tissue, thereby minimizing the effect for electrical failure and immune response. As a screen of biocompatibility, we grow smooth muscle cell on the top of this whole device and check the viability assay. As you can see, this green thing shows the live cells, where the small red one shows the dead cell. And the microfilament of the muscles, which are red ones, is skeleton of the cells, and the blue is the nuclei, and the green point shows the local adhesive points. And you can see that from the scanning electron microscopy image, the cells spread all over the device without any agglomeration. And you can, again, see the healthy cells numbers over time with a controllable setup and on the top of the device, which suggests there is no detectable toxicity over time. This is the in vitro evaluation. For this case, actually in this step, I'm talking with my device and I'm asking my device if I value with certain displacement and frequency, how much voltage and current that I will get from you, so that I can know the power generation and go for the in vivo evaluations and tests. So to do this step, I designed the bending stage, which is computer controllable system. And we clip the two ends of the device and bend it with certain displacement. And in this case, I work closely with mechanical engineers at Northwestern University, and we come up with a theoretical model as well. As you can see, experimental results capture very well by the theory. And we can see the strain mapping on the top of the PZT while we bend it, and it yields a buckling shape when you bend it like that. And when you bend it, you get a positive response, a voltage and corresponding current. And when you release it, again, because of the dipole changes within the crystal, which I mentioned before, you get a negative response, which means that your device is talking with you and it's giving you some power over time. And not only producing voltage and current, we can also store this energy, because we don't need to use this energy all the time. So what I did, I first imagined this cartoon where I have my PZT-MEH and then a rectifier to buffer the energy and micro battery. And then I fabricated it. It's exactly the same. So now you can see the voltage output across the microbattery over time, over cycling time when you cycle the device, you can see the voltage output increases and coming a threshold volt, which is 3.6 volt for this particular microbattery. And when you focus this small red region, you can see the expected step size behavior during the bending and unbending as we showed before. And later on, I work with heart surgeons at the University of Arizona, and we affix the devices on beating heart with the medical sutures at 3 different focal points. And we pick 3 different locations, epicardial locations, such as right ventricle, left ventricle, and free wall, to find the optimum location which gives the maximum output power. As you can see from RV, LV, and free wall results, RV yields better voltage responses than the other cases because I learned it. RV is a box shape with concave free wall, and it ejects the blood primarily by shortening its free wall, thereby increasing more strain to the PCT, my device, so that voltage and current will be more than normal. Not only this, some of ours are big, some of are very tiny, so our heart mass is different. So to mimic this, we picked 2 different animals, bovine and wine. And for this particular research, bovine heart was twice mass than ovine. And as you can see, once your heart is big, your extension and relaxation is more than the small heart. So again, the same phenomena, you give more strain to PCT and create larger voltages compared to, in these 2 cases. Bovine yields more voltage than the ovine case. We also did more experiments. We stimulate the heart with the external pacemaker, and also a sort of drugs which is called the vitamin, just increase the force of contractility of heart and also frequency to check if the device is stable for the severe cases. Not only heart, lung and diaphragm are also optional organs that you can generate power. From the respiratory movements, when you inhale and exhale, again the strain occurs on the device, and you can get voltage, negative and positive voltages, as we observed from in vitro and in vivo tests. Later on, as we cannot walk with open chest, we have to close the chest. So here we show that when the chest is open and closed, still our voltage output from the device stable, and there is no degradation over time. And here is the suture part that I learned, and I sutured this part, so it's very special for me. I always point it out, when I do a presentation. And in this concept, as we can get enough voltage when the chest is closed, now it is important to check the magnitude of the power that you can get from the device. By engineering the device layout in such a way, with different PCT and image on the top of each other, you can boost up your power generation, because they are in capacitor form. So basically, if you connect 2 capacitors in a series form, you increase your voltage output. Here, with 5 PCT and image on the top of each other, we can generate time average power density as large as 1.2 microwatt per centimeter square, which is sufficient enough to drive a modern pacemaker. And as a conclusion, I show you a biocompatible, ultra-thin, first of its kind, mechanical energy harvester from the internal organs. And it's conformal, and we can use it as a multi-layer configurations to generate sufficient energy for different applications, not only for cardiac pacemaker as well. And we can generate and store the energy even at your chest as closed. So I thank my PhD advisor, John Rogers, and research members, my collaborators from University of Arizona and the Northwestern University, and also my undergrad team at University of Illinois. Thank you.
Thank you. If I would have known and seen the presentation before, which I had not, I would have said the pacemaker meets its patch, not its match. So that was very good. Excellent work, and we really look forward to seeing you back here again for our innovation series. Right now we're going to take a little break, network a little. We'd like to get back here for the competition award ceremony that we're going to do at 2:50. So if you get back here by 2:45, that'd be great. Thanks for all your attention, and then we're going to wrap up with our keynote speaker. Thank you.